Welcome back. We're going to talk about properties of convex functions and how these translate into different convergence rates for gradient descent or the subgradient method. Again, our motivation is these two very simple functions. F of x is equal to 3x squared plus 4x minus 2, and something like f of x1, x2 is equal to 10 times x1 plus absolute value of x2. Or even more simply, just the absolute value of x. So looking at gradient descent or subgradient method and how these perform on these two different flavors of examples, we saw some very important and key differences. First of all, gradient descent improves at every single iteration as long as we take our step size to be smaller than 1/6. This is not necessarily true for subgradient descent, and you can verify this by actually computing subgradient of this function here and checking that at certain points you may take a step that actually increases f. So we're always going to talk about the subgradient method because it's not necessarily a descent algorithm, and gradient descent. That's this first point that we saw for these two examples. The second point is that gradient descent had this self-tuning property for this polynomial, 3x squared plus 4x minus 2. So in other words, the gradient descent algorithm here told us that xt plus 1 is equal to xt minus my step times 6xt plus 4. So let's look at this 6xt plus 4. We know that the solution to this problem is equal to minus 2/3. Now what happens to 6xt plus 4 as we get closer and closer to minus 2/3? Well, it gets closer to 0. So this allows us to take a step size eta that doesn't depend on the final error that we want, and this will naturally slow down. This iteration naturally slows down as we get to the optimal solution. We can see this in a picture as well. The gradient is big when we're far out away from the solution, but as we get down, the gradient gets flatter and flatter and flatter. Let's compare that to the absolute value. What's the value of the gradient very far away? Say out here. It's equal to minus 1. What's the gradient arbitrarily close to the optimal solution, which is 0? It's still minus 1. And this is why we ended up seeing this overshoot. We ended up seeing this overshoot property if you're doing a subgradient method with a particular step size eta. So if you want very small error, your eta better be very small. So this is a stark difference. Again, I'm going to just summarize this by saying that this function on the left has what I'm going to call the self-tuning property, and the function on the right, the absolute value, does not. Let's go back to, again, our expression for the gradient update for this polynomial. What else do we see that helps us? We see that when we're very far away from the solution, minus 2/3, so when xt is a very big negative number or a very big positive number, the value of this gradient is actually very big, and that helps us. That's exactly what we need when we're far away. It's a perfect coupling to this self-tuning property. It's saying that when you're very far away, even for any eta that you choose, a fixed eta that doesn't scale with how far away you are, you're going to naturally take a very big step towards the optimal solution. How about the absolute value function? Well, no matter how far away we are, we're stuck with a gradient value that's an absolute value equal to 1. So all you can do, no matter how far away you are, is make step size eta. That means that if you start twice as far away, you are forced to take twice as many steps. For the polynomial function, however, that's actually not the case. So these are three important properties that directly translate into very fast linear convergence for our first polynomial function, f of x equals 3x squared plus 4x minus 2, and much, much slower convergence for our function f of x equals absolute value of x. And we're going to formalize these ideas that are behind these three properties. We want to formalize the idea of self-tuning, etc. And then we're going to show what good properties does it directly translate into for the gradient descent iteration for functions that have these properties. We need to mention that we have some basic assumptions we're going to make throughout. So the first assumption is that we don't start infinitely far away from x star. And a lot of the bounds that you'll see that we're going to give, we will see a term that looks like x1 minus x star in the bounds. This is a measure of how far away we start. Of course, we can't know this exactly because we don't know x star. But for typical application, we just need to know some upper bound so we have an idea of what the convergence looks like. We will also assume that our functions are not infinitely steep. And you may say, well, that doesn't sound too reasonable because what about functions like x squared? This is a very natural function, and x squared, as you go out here, you do get infinitely steep. But again, this relates to the first point here. We're really going to minimize this function where you have to start from somewhere. And wherever you start, you're not going to be infinitely steep. And in particular, wherever you start, unless you're doing something like taking too big of a step size, you're not going to go farther and farther and farther out where the function becomes infinitely steep. And then you might say, very correctly, that well, it's not just functions like x squared that get infinitely steep. I might have a function like 1 over x. This is another fine convex function and looks something like that. So perhaps we want to minimize this over some region. Again, the answer is very similar. We don't need to go infinitely far to get infinitely steep here. We just need to go towards 0. But we're not going to start exactly at 0 because this function is not defined at 0. And anywhere you start, you can see that gradient descent is going to push you away from that region of infinite steepness. So unless you're doing something like taking an inappropriate step size, which is causing you to diverge, we're not going to have to deal with this. So these are two basic assumptions that we're going to see throughout. Okay, so let's talk about smoothness. So the motivation here, it comes from the idea of self-tuning. Remember, we saw that what we used is that the gradient of f of x in absolute in length, norm, goes to 0 as x goes to x star. What we really need here is that the gradient doesn't change too much when x doesn't change too much. We can write this as the gradient of f of x minus the gradient of f of y. How does this compare to the change between x and y? And saying that the gradient doesn't change too much when x and y don't change very much is exactly like writing something like this. This is saying that the gradient is smooth. The gradient is continuous. And in particular, the word smoothness in convex optimization and convex analysis has a very specific meaning. And I mention this because in other fields of math and science and engineering, smoothness may mean different things. But smoothness for convex optimization means specifically what I've written here. A function f is called beta smooth, or smooth with parameter beta, if, and I'll write the formal term here, its gradient is Lipschitz continuous with parameter beta. Lipschitz continuous means exactly what I've written above. let me just repeat that since it's part of the definition here. So gradient of f of x minus gradient of f of y is less than beta times x minus y. So we need to see now, how is this useful? What is this going to do for us? So we're going to see that this is going to translate into a very useful property for convex functions. And in particular, it's going to tell us that every smooth function can be approximated above by a quadratic. And this is very useful for us. And we'll see exactly how that translates into improved bounds. Now, this slide and the next slide I'm going to spend in order to derive this relationship. So we have a little bit of work to do on the way. So first I'm going to show that if f of x is smooth with parameter beta, if f of x is beta smooth, then the function beta over 2 times norm of x squared minus f of x is itself convex. Now note that in general, minus f of x is not going to be convex. If f of x is convex, minus f of x is convex only if f is linear. Otherwise, minus f of x will typically fail to be convex. Just think about a parabola. If you flip it, then it's not convex. So this is saying that this function is convex. So let's see how this goes. So let's call this function g of x. And we're going to show that g of x is monotone. So first, recall that if a function is monotone, then it's convex. So let's see why g of x is monotone. So let's write down what we need to show. So I need to show that the gradient of g of x minus the gradient of g of y, dot product with x minus y, is greater than or equal to 0. So this is what I want to show, and this is equivalent to convexity. So let's see how we can derive this relationship. So just plugging in what gradient of g is, and rearranging a little bit. So gradient of g is equal to beta x minus gradient of f of x. Gradient of g of y is beta y minus gradient of f of y. Grouping those terms together, this is equal to beta times x minus y minus the gradient of f of x minus the gradient of f of y. That's this term, that's the first term in the dot product. Dot product x minus y. Now, this is equal to beta times x minus y dot product x minus y, which is just x minus y squared, minus what's left, which is the gradient of f of x minus gradient of f of y, dot product with x minus y. Now I'm going to use Cauchy-Schwarz. So remember that uv is less than or equal to the norm of u times the norm of v. So I'm going to replace this with something bigger by using Cauchy-Schwarz. But if I'm subtracting something bigger, what's going to happen? I'm going to only make this potentially smaller. So this is equal to beta times x minus y minus gradient of f of x minus gradient of f of y times the norm of x minus y. Now, why did I do that? How does this help me? What are we trying to use here? Well, I only know one thing about my function f, other than the fact that it's convex. And the only thing I know about my function f is that it's beta smooth. And so I want to use this property. This property. And now we can see that we can use it. So again, I'm going to replace this term here with something potentially bigger. And if I'm subtracting something bigger, I have the right inequality. So this is greater than or equal to beta times x minus y squared minus beta times x minus y. This is the definition of smoothness, times x minus y. And this is finally equal to 0. So what did we show? Gradient of g of x is monotone, and that, as we've shown in the past, implies that g of x is convex. Okay, so we've concluded this. Now let's see what this gives us. So we just showed that g of x equals beta over 2 times x squared minus f of x is convex. Now we can just write down what the consequence of convexity is. So remember that something is convex if I can globally underestimate it with a linear function that touches it at a particular point. In other words, by our definition of convexity, g of y is greater than or equal to g of x plus the gradient of g of x times y minus x. Let's plug in what g of x is. This tells me that beta over 2 y squared minus f of y is greater than or equal to beta over 2 x squared minus f of x plus the gradient of g of x, that's beta x minus gradient of f of x times y minus x. We know that this holds. But then if we rearrange this, and in particular, if I bring f of y over to the right and bring everything else over to the left, I find that this tells me that f of y is less than or equal to f of x. Note the sign is going to change because f of x goes over and everything else goes over. I'm going to erase those arrows. I think they're probably just cluttering things unnecessarily. F of y is less than f of x plus the gradient of f of x times y minus x plus beta over 2 y squared minus beta times xy minus beta over 2 x squared plus beta x squared. And grouping all these terms, you see that what I have on the right is just f of x plus gradient of f of x times y minus x plus beta over 2 times y minus x squared. So it's worth looking at this carefully. What do we have here? F of y, I'm just rewriting this a little carefully, f of x plus gradient of f of x times y minus x plus beta over 2 y minus x. This looks familiar with something that we've seen over and over again, but it's different in some key ways. So the general inequality for convexity I've written up here, it's that a function is greater than or equal to its linear approximation. But here we have something different. We have the inequality is reversed. It's saying that the function f is less than or equal to the first term, which is the standard linear approximation that we see, plus a quadratic term. So the picture here is that if I have any convex function that's smooth, at any point I can fit a quadratic on top of it. That is basically the definition of smoothness. One quick thing that's worth mentioning, if f is twice differentiable, recall that the definition of convexity tells me that the Hessian of f is positive semi-definite. But now, if in addition f is smooth, we have that this Hessian is upper bounded by beta times the identity. Okay, let's look at our two examples here. Our absolute value function. Well, we know that this isn't smooth because it has this point, but let's see how it compares with this definition that we just derived of trying to fit a quadratic on top. Now, at this point, we can certainly fit a quadratic function. But how about at this point at the origin? And you can see that at this point, so at the point x equals 0, no quadratic upper bounds the function. Because no matter how steep you make your quadratic, at the very, very bottom, we know that the slope is 0. So initially, for very, very small x away from 0, it's going to open up slower, more slowly than the function that just grows linearly. And so there's no way we can do this. So this is another way to think about the failure of smoothness for this function. It's also worth going back to another very simple function we've looked at, the general quadratic, f of x is equal to x transpose qx. We could add a linear term and a constant term here, but these don't change anything about the curvature, which is really what we're talking about here. So what is the smoothness parameter? I'll leave this to you as an exercise, though really it's a direct application of what I said on the previous slide about the Hessian. F of x is beta smooth for any beta that's greater than or equal to the largest eigenvalue of q times 2 here. 2 because we're going to take when we take the Hessian, it's twice q. So twice lambda max is the smallest beta for which our function is beta smooth. Okay, so this is so much for smoothness. What was the other property that we defined, that we needed? We needed, when we're far away, this is our function, we saw that when we were far away, the gradient was big. So what corresponds to that property? Let's define strong convexity and see how this relates. A function f is called strongly convex with parameter alpha if the function g of x equal to f of x minus alpha over 2 times x squared is convex. This is the definition. So note that it's very similar, but somehow flipped from our consequence of smoothness. Now, if g of x is convex, let's plug in again the direct inequality of convexity, the main inequality of convexity, g of y greater than or equal to g of x plus the gradient of g of x times y minus x, and see what this gives us. This tells me that f of y is greater than or equal to, f of y minus alpha over 2 x squared is y squared is greater than or equal to f of x minus alpha over 2 x plus the gradient of g. What's that? That's the gradient of f minus alpha x times y minus x. Rearranging terms, I find that this tells me that f of y is greater than or equal to f of x plus the gradient of f of x times y minus x plus alpha over 2 times y minus x squared. You need to do a little bit of rearranging and group the quadratic terms to see this relationship. So what does this tell me? This is standard convexity, and this is saying it's actually stronger. And so This is standard definition of convexity. And strong convexity adds this term. So in terms of our picture, this is saying that we can fit a quadratic underneath. So unlike smoothness, which was telling us that f of y is less than or equal to a quadratic, strong convexity is saying that f of y is greater than or equal to a quadratic. So it's basically giving you a guarantee that your function grows when you move far away from the optimal solution. Not only your function, but also the gradient of your function has to grow, because if you're lower bounded by a quadratic is very steep when you go far out, and therefore your function must also be very steep when you're far away. And that's exactly what we used, the property we exploited, to make very fast progress when we were far away from the optimal solution. It's also worth noting what this tells us about the Hessian. So if f of x is twice differentiable, then f of x is alpha strongly convex is equivalent to the Hessian of f not being just positive semi-definite, but being greater than or equal to alpha times the identity, which is exactly the same as saying that the function f of x minus alpha is strongly convex. Is convex. And we can see this directly from the definition. If we plug in what it means for G to be convex, it means the Hessian of G is positive semi-definite, but the Hessian of G is exactly the Hessian of f minus alpha times the identity. So we've seen the quadratic example for smoothness. In this case, f of x is alpha strongly convex, where alpha is equal to twice the smallest eigenvalue of Q. We've been talking about strong convexity, and everything I've drawn has been smooth and strongly convex, but it's possible to be strongly convex but not smooth. So for example, if you take the maximum of two quadratics, that function is this, and you can check that this function is strongly convex, but it's not smooth because of this point. You can check it actually technically with the algebra, or you can just verify that you can fit a quadratic that underestimates at every point, but at this point here, you cannot fit a quadratic on top, so it's not smooth. And we can also be smooth, but not strongly convex. In particular, if you're flat, and then you curve up, and you're flat again, then this function is smooth, but not strongly convex. Next time, we're going to look at how smoothness and strong convexity translate into additional useful properties for convex functions. And we'll pick it up next time.